For decades, software engineering relied on a simple premise: code executes exactly as written. But when you deploy an autonomous AI agent, predictability vanishes. In a standard application, the architecture is linear. A user triggers an action, the server processes the request, queries a database, and returns the data. Because this path is fixed, standard monitoring tools easily map the execution, logging the precise milliseconds it takes to move from point A to point B to point C. An AI agent operates on an entirely different premise. Instead of following a predetermined script, the system receives a goal and then independently dictates its own execution path within a continuous loop. It might invoke a search tool, evaluate the results, determine it lacks context, and decide to loop back to query a completely different database, all without human intervention. This recursive reasoning breaks standard telemetry. To a traditional monitoring setup, this multi-step decision process registers as a single, opaque block of high latency. This creates a critical blind spot for engineering teams. If you cannot see how an agent arrived at an answer, you cannot trust it. Without that trust, an experimental prototype cannot safely migrate into a production environment. Collecting isolated metrics, like total token counts or endpoint uptime, provides no value if you cannot correlate them directly to the specific sequence of decisions the agent was executing at the time. When an agent fails in production, you encounter a non-deterministic fault. Looking at a standard dashboard, it is impossible to know if the underlying model hallucinated, a third-party tool timed out, or the agent trapped itself in an endless logic loop. To run these systems at scale, you must force accountability onto every agent step, transforming the black box into a transparent operational timeline. The solution is a correlation-first architecture. This requires a system designed specifically to fuse multiple independent streams of telemetry into a single record of the run lifecycle. To close these visibility gaps, we need to capture 4 specific signals from every run: the execution traces, the mechanical performance of tools, the exact token cost, and the final response quality. Unless you can explicitly tie the compute cost to the specific execution path that generated it, an autonomous agent is an unmeasurable liability disguised as a product. Let's map out this architecture from the ground up. Every action begins with a standard entry point, the user request, which flows directly into the core reasoning cycle. This central node is the agent loop. It acts as the primary orchestrator, dictating timing, routing, and overall flow. To track what happens inside, we capture a distributed trace for every discrete thought or action, logging it as an OpenTelemetry span. This node captures the exact start time, end time, and success or failure status for that specific individual run. By capturing these sequential spans, we flatten the chaotic, recursive logic onto a strict, readable timeline for engineers. But an agent's utility comes from its ability to interact with the outside world. We must track exactly how it reaches out to external systems. The architecture routes agent actions through a Model Context Protocol, or MCP, bridge. This bridge acts as a universal translator. It abstracts the varying complexities and authentication methods of different third-party APIs away from the core logic of the agent. From the bridge, the system connects directly to the specific MCP tools the agent has permission to invoke, whether that is a database query or an internal file search. Merely knowing a tool was called is insufficient. We have to measure the mechanical execution of that request in total isolation from the language model's processing time. To do this, we attach a dedicated performance tracking layer directly below the tools. This node captures the raw data of the external interaction, connection latency, API success rates, and exact HTTP error codes. This strict separation is vital. When an operation times out, engineers can instantly check the network layer, ensuring they don't waste hours debugging an LLM for a delay caused by a slow external API. By combining the OpenTelemetry spans with these isolated MCP tool metrics, we secure complete temporal visibility into the agent's actions. Securing operational stability solves the engineering problem, but business viability is an entirely separate challenge. Unchecked, continuous AI compute scales costs aggressively. To manage this, we introduce a financial layer designed to map compute behavior directly to actual dollars. This requires strict granularity. The system continuously logs prompt and completion token counts, isolating the data per individual request and per user session. Tracking these metrics provides the exact data required to calculate the return on investment for any specific autonomous workflow. Yet, fast and cheap execution holds zero value if the agent's output is factually incorrect or fails to solve the user's problem. This requires an automated quality assurance mechanism running in parallel. The online evaluator analyzes and scores the quality of the agent's response dynamically, right alongside the execution cycle. However, 4 separate streams of data cannot solve a multivariable failure. If these logs remain in isolated silos, an engineer cannot query the relationship between a specific tool's latency and the resulting cost spike. To execute the correlation-first mandate, all 4 data streams must converge into a single repository, the Observability Store. This database can be intentionally lightweight, utilizing software like SQLite, because its primary function is defining relations, not managing massive data scale. The correlation mechanism itself is straightforward. All disparate data points are joined together by a single shared session ID. Because the data is linked, you can instantly run a query to determine exactly how many tokens were burned by a specific failing tool across 1,000 unique runs. The Observability Store acts as the central nervous system for the platform, turning raw logs into precise, actionable intelligence. This flowchart displays the complete verified architecture, tracing the path from the user request through the agent loop and down into the Observability Store. The store feeds 2 critical outputs. The first is a command line interface and human-readable reports. MLOps engineers rely on this interface for instant root cause analysis on failing production runs, drastically reducing mean time to recovery. The second primary output feeds directly into bulk analysis and offline benchmarks. Here, engineering teams can test smaller, cheaper language models against historical session data. If evaluation scores hold steady, they deploy the cheaper model to safely optimize costs. With a lightweight, asynchronous design, teams can prove their observability patterns early, ensuring correlation logic works before committing to massive enterprise monitoring backends. Moving to production requires treating the AI agent as a system with measurable components, rather than a black box managed by trial and error. Deploying enterprise AI demands rigorous systems engineering. A correlation-first observability layer is the mandatory baseline to achieve true agent autonomy.